I'm Yuriy Reznik. I'm with Brightcove. I run research group, and I'm going to show some formulas, but I'll try to not to dive too deep into it, and try to use simple words to explain what I'm doing, and hopefully it will be understandable. The outline of the talk is as follows. I'll talk about multi-codec streaming, and before I start talking about multi-codec, I'll introduce some basic concepts, things like what is IBR streaming, models of codecs, streaming clients, ABR ladders. Last time here I spoke at length about CDN performance and streaming. That is kind of relevant, but I'll skip details. And then I'll talk about design of quality optimal ladders for ABR streaming. And we will look at example case of using single codec design, which is simple and well understood by these days. And then we'll look at a system with two codecs. And that will actually have very interesting connection to what is known in information theory as multiple description coding problem. But so there will be a little bit of fun on theoretical end, but then a last few slides will be devoted to what it all actually means in practice, and I'll talk about what's actually implemented, deployed, and give some real-world examples. So let's start with ABR streaming. Basically, in present world, we're talking about, in present time, we're talking about HTTP-based ABR streaming delivered by means of protocols such as Dash or HLS. And what usually is done in these cases is that content is encoded at several bit rates, right? Then each bitrate stream is called rendition. Usually, the composition of those streams is usually called ladder. Then each of the streams is chopped in segments such that clients can switch between those streams at segment boundary at certain interval, which is typically segment length, which is could be 2 seconds, 6 seconds, and so on. Fairly fine-grained switching, I should say, and then content, which is a composition of such segments plus a manifest file declaring all of them, goes to origin server. And from that moment on, delivery and scaling is done by CDNs, which of course is a highly scalable and cost-efficient way to do things, and conceptually simple, which is important. And then the logic of actually pooling these segments, understanding what current bandwidth is, and then deciding what of the next streams to pull next is happening on a client. And this way, clients could predict bandwidth, and if they see that there is, for example, one stream at 1 megabit and another stream at 2 megabits, and the bandwidth is already 3 megabits, then perhaps it's time to switch to 2 megabit stream, because you could pull it at this bandwidth reliably, and the quality will be better. So the idea of clients is to deliver uninterrupted performance and good quality. So it works somehow in most of cases, and the objective of the talk is to kind of think about what it is and how to design it optimally. So some basics. Of course, what usually is an input for streaming is the content. The content could be of different complexities. It could be, for example, cartoons. It could be high-action sports, and you need totally different bit rates in both cases. With cartoons, you could encode them at 1 megabit at 1080p. It looks fantastic. With sports, maybe 10 megabits is not good enough, depending on a kind. Codecs, nowadays. There are many of them, and they differ in efficiency. For example, HEVC in most cases is considered to be better than H.264. AV1 and VVC, which is coming, even better. I heard recently that AV2 is going to be coming next. So the world is going to be even more merrier as time goes on. And what is important is that the difference between those codecs are also content dependent. So for ultra simple content, perhaps H.264 and the difference between H.264 and HEVC is not that significantly. For complex content, it could be a totally different story. And same with others. And if the difference is significant, it's great. It makes sense to switch to the codec. If the difference is not that significant, we are in gray area where we really need to think. Now, there are also many different quality metrics, but actually none of them is really good. So there are very simple things like MSC, PSNR, which basically measure average amount of noise. SSM does normalization of this noise by local energy, which basically maps it in domain of contrast or contrast sensitivity, which is a unit that is more closely mapped to mechanics of human vision. But it's still very basic and nowhere close to realities of how perception works. VPD, visual difference predictor, and PQR, which is a Tektronix metric based on old Lubin's model. Those are kind of more advanced metrics, but you need to either invest time in developing them or pay a lot to Tektronix to use them. And then, of course, there is VMAF, which fuses several basic metrics, but it's still work in progress to best of our understanding. It works in many cases. It actually fails in some others. For example, if you have clean input and you're comparing against your output, the results are more or less okay. If your input is bad, VMAF could be arbitrary, misleading in terms of what it tells you about quality. So now, but regardless of which metric you're using, codec and content, if you take the triple of all of them, you actually can characterize performance of that system, and that is done by basically quality rate function. What is quality rate function? Is basically you encode video at several operating points, and then you connect those points by a certain model to say what is the space of achievable regimes or operating points could be. And in the example on the right, I'm showing an exercise where I took cartoon-like content as well as a complex sport type of content, and they encoded them with H.264 and HEVC at about 5-6 points at CRF, and then I connected them with very simple models that is shown below with 2 parameters, and you see that that model actually fits pretty well. And so this is kind of what you could say about content plus a codec plus metric. You could just create models that tells you what is the space of achievable trade-offs is if you encode it. Now, another thing that you need to quantify if you're trying to design a system optimally is you need to understand what is the model of network. And to understand what network you're working with, you really need to start with logs, either from players or CDNs. Look at statistics. For example, below I'm showing histograms of bandwidth collected by Brightcove analytics module, and then you could also model them. So on the right, again, it's a theoretical example. I took measurements of network from LTE network with 2 different types of loads, and thrown a mixture of 2 array length models, and there are 3 parameters, and it actually fits pretty decent to the experimental data. But again, important thing is that information about important information for design of ladder about network could be actually reduced to network model, and that is basically distribution function. It tells you what is the probability that your bandwidth is X, and for example 2 megabits or 1 megabit or 10 megabits. And now, last model that we need, and that is a model of a client. And a client, of course, is switching, right? And it is switching based on bit rates that are available on the ladder. And it is switching such that giving the available bandwidth or estimate of available bandwidth, it tries to pick bit rates that will be sustainable, such that you could load rendition at that bit rate and you're not going to run into buffering. So the simplest way to think about it will be to say, okay, well, if ladder will pick the highest bit rate that is equal or below that available bandwidth, that will be sustainable regime, and that's a viable approximation of client behavior. Of course, in practice, it's much more complicated, but this simple model actually works for the purposes that we will be using it for. And there are two ways to think about it. The first plot shows the selection of bitrate based on available bandwidth, and the right plot shows what happens with achievable quality in that case. So it basically, from continuous quality rate function, which is sigmoid type of function, right? We end up with a staircase approximation of it. So effectively, we're quantizing that quality rate function to n points, which becomes our ladder operating points. But now, if we know this client model, right, and that is R selected of R as a function, and we know network models, then we could, of course, describe what would be the average bit rate that a client is pulling during the streaming session and the average quality. These are shown here. It's a simple integrals. Of course, in practice, if you work with histograms, those become sums. But you know, the models could be you know, functions with some mechanics in them. But this is a basic concept. Now, so
from the selected bit rate, you're showing that
right.
The quality.
So quality rate function. It was just a second. It was here. So basically, pick any metric you like, encode your content at several operating points, and then fit that with a model that will predict you what would be the quality according to this metric for this content and for this codec that will be achievable at that bit rate. So it's a model that gives you a space of all possible achievable.
The qualities are not subjective qualities. The qualities are based on those models. Which model you choose.
Exactly. It's which metric you choose.
Which metric you choose.
It actually could be objective quality. You could actually do a MOS score, and you could record. So those points that I'm showing here, these are experimental points that you put, and then you fit a curve of any suitable shape that fits them well. And that gives you the input to the algorithm. So in this case, the model is actually the sigmoid type of function. It's actually one of the classical sigmoids used in exam dynamics and neural networks and similar areas. So it's a very kind of standard sigmoid model. But it fits pretty well for SSM and codec behavior. Now, so that gives us quality numbers, and then we plug in client model, and we get estimates of average rate and average quality. So what we can do next with this? Well, now we could kind of think about whole streaming chain, and of course we start with source, then it goes through encoder. After encoder, you have a ladder, right? You have endpoints with rate at each and quality at each, Ri, Qi. So you have pair of numbers there. And then you go through a client, which effectively does rate selection plus decoding. And as described previously, from that client model, we could express average rate and average quality that goes to the end, at the end of the system. So those average rate and average quality is average quality that's delivered to the user at the rate that was consumed from network. Now, if we think about it this way, and we have all the models in place, then one problem then can be immediately posed is, given certain number of rendition n, quality rate model, network model, what would be the set of rates from R1 to Rn such that the quality that will be achievable by the system is maximum? Why there will be maximum? Well, because we are balancing between two things. We are balancing between probabilities of how many viewers will be watching content versus the rate and quality that's achievable on each. So there is a pretty strict optimality point in that situation. And in fact, if I throw all the models that I was showing before to Mathematica and run maximize, then this will be the ladders that I obtain as a result of it. And what we can see is that for easy content, of course, the bit rates will be different than for complex content, right? HEVC bit rates will be generally slightly lower than H.264 bit rates, right? And if we repeat this exercise for network 2, the results will also be different. So that really tells you that this is an optimization problem, and you really need to take into account both content, codec, and network as inputs. You can't solve it optimally if you disregard either one of them. So it's this is where we stand. So this is optimality problem for first for a single codec system, and you could design it for either codec. But now what's going to happen if we start looking at systems with two codecs? And I'll spend most time on this slide, actually. So consider a system where we now have two codecs. There is H.264, and there is, for example, HEVC. And of course, there will be clients that can decode H.264. Most of clients these days can decode H.264. Some clients can decode HEVC, right? And some clients can not only decode HEVC, but they also can switch between HEVC streams and H.264 streams seamlessly as they pull streams. So you could, and one good example of clients of this kind is actually Apple devices. So all new Apple devices, iPhones, iPads, you throw the mixed ladder renditions where some of them H.264, some of them HEVC, they will switch between them. And they will switch seamlessly. And what it means? Well, if device can decode only H.264 or only HEVC, then of course they will be dancing along the curve of that corresponding codec. For example, green curve here shows HEVC, red curve, it's a quality rate curve, shows H.264, and then the point that, for example, HEVC only device will be picking will be only green points. It will be switching from this point straight to another HEVC point, and so on. But if it only switches between those points, it might actually be missing something. If we design ladders, both of these ladders, in such a way that you put renditions of H.264 streams in between two HEVC streams, and you place that point wisely, there could actually be intermediate reconstruction level that makes sense. It will be better quality at a better rate, but not quite large gap compared to case when you are switching straight from one HEVC rendition to another HEVC rendition. Why is this extra switch is helpful? Well, because then you can approximate network behavior better. You could stay closer to actual network bandwidth as it is available. You could pull more bits and deliver better quality once needed. Well, now, of course, you might ask questions. Why in the universe this is even possible? Or when it is possible that you have two codecs and you still have those intermediate steps that make sense. Well, it is possible when the difference between these codecs is not that big. For example, if this will not be HEVC, it will be VVC, and the gap between codec is between rates of two codecs is factor of 2 or 3, then probably there is no point of switching between them. There will not be any more intermediate points that will be meaningful. But if the gap in performance of the codecs is not that significant, if it's like 20%, it turns out there are a number of useful additional operating regimes that could be found out. And if there is the category of devices that can switch between those codecs, they can utilize it, and they can achieve better quality using fewer streams.
So this third type, is that practically being Is the third thing practically being used?
It is
in the
Apple
world right
devices.
now? Brightcove?
Apple devices.
No, Apple devices, I understand Apple
Right.
devices can do that, but are people doing that? Are they writing applications where they are switching the ladder, they are switching the codec between the ladders?
Precisely.
It is worth mentioning Apple explicitly say in the spec now, do not do this. The HLS offering guidelines say pick a codec and stick to it now. It used to say the codecs, the guidelines at Apple say in offering, say don't do this. It used to say you may do this. It now says you should not do this. Within the last 6-8 months, they've changed it, and I don't understand why. I assume there is certain devices that have issues.
In practice, they work, number one. In practice, they work. Number two, actually, there is a growing class of devices that is switching, and actually the trend is to enable all devices switching. As you well know, there is an effort on MSC 2.0, which is enabling switching between different codecs, and we are entering in the world. There will be more codecs, and switching between them will be even more crucial. So let's see what Apple guidelines will say in another 3 months. Yeah, they had tendency of switching in the past. But as a matter of practice, in fact, today all Apple devices can switch seamlessly, and it works pretty well. But there is another question, please.
Working in this way, do you necessarily compromise the optimality of the 264 ladder because you're adding another constraint?
So we will get to this. So it will be a joint ladder optimization problem where there was another question, right? No? Okay. Okay. So, but I just wanted to make sure if we understand what I'm talking about. Okay. So there is a way to create 2 ladders jointly such that there will be intermediate points allowing clients that can switch between codecs to operate more efficiently. And if we start exploiting this property, where we can go and what would be the effects. So deployment model, the safest way to do it is to have edge support where there is a device detection, manifest filtering logic such that if device is understood to be a legacy device, only H.264 renditions are left. If device is understood to be a new device capable of HEVC but not switchable, only HEVC renditions go. And if it's Apple device, you leave everything there. And of course, mechanics of doing this with HLS and Dash are slightly different. In HLS manifest, you could order variant streams by bitrate, and that's enough for client to be able to pick them. In Dash, you should create separate adaptation sets, but then there is a supplemental property descriptors that you could use to say that you can switch between them. Now, this is the...
You weren't going to have a lot of equations.
This is very
It's not
easy.
going to be a test.
This is very easy. So I've shown a similar picture before where there was just one.
I'll let you go first next time.
Okay. There is a source, there is an encoder, and there is a client, right? In this case, there's still one source, luckily. There are 2 encoders, and there are 3 types of clients. And what is shown here is that after first encoder, we have first ladder. After second encoder, we have second ladder. In the middle, to the joint decoder, we have a union of both ladders, so both ladders are available. And what is shown as average quality is achievable are formulas explaining what would be average quality is achievable at the end of each client. And Q sigma is actually the average, blended average of all those quality values with population parameters. So
you're solving for optimal dual codec
Exactly.
ladders in some sort of space where you're trying to find the local maxima
exactly.
in terms of quality in aggregate.
Exactly. Exactly. So the final aggregate expression is actually this weighted sum of quality is achievable by all clients And weights are basically population weights or population probabilities. So P sub 1 is effectively fraction of clients that can only decode, for example, H.264. P sub 2 is HEVC, and 3 is a switchable codec. And of course, the objective is to find a mix of sizes of profiles that give you total number of renditions to be same, and then rates allocated to each codec such that the quality is maximum. It's a kind of generalization of previous problem. Now, the beauty of all this is that there is absolutely nothing new in this from mathematical perspective. It was all well known as so-called multiple description coding problem in information theory. And in fact, there was even a paper by Azarov in the 1980s specifically studying systems with 2 encoders and 3 receivers. It looks exactly like what I just shown you before. With fewer formulas, but basically it was studied.
So did you know this when you did that, or did you, did you derive your previous idea from this?
No, actually it was differently. I solved that problem, and then I recalled that many years ago I saw this paper and that particular picture looked similar.
And you just happen to have it lying around on your desk. It's astonishing.
You know, I was part. I was
AT&T 1980.
Exactly, it's a Bell System Technical Journal. So, but this is a famous problem, and the interesting part about it is that it is beautiful theoretical concept, and it had only periodic and occasional surfacing in history of people actually trying to do something with it in practice. And in most cases, it didn't produce anything useful, or there were found different approaches to do things more efficiently. Somewhat close to this problem is so-called scalable coding, but scalable is much simpler variety of it. So this one is more interesting. And but in this case, it sounds like we found application. And of course, the difference between theory is that in theory, the biggest point of amusement was the fact that if you do this joint decoding, then you actually could achieve quality or rate distortion trade-offs that are better than from 2 separate decoders. And that is usually described by so-called achievability regions. And usually the theorists stop right there. Their job is done at that point. We found that this is a fact. That it's possible to derive better quality. Of course, in our case, we need to try to extract some utility from it. So this is why we connect all the outputs to a common output, look at the mixture of them, and try to run optimization on top to find out what would be the best ladders. And here they are. So this is network 1, easy content. Probability of devices that can decode HEVC is 0.4. Probability of devices that can only decode H.264 is 0.2. And the rest, which is 0.4, is the hybrid client. So that's the anticipated delivery scenario, which coincidentally is similar to what US looks like if we think about mobile. About 40% of Apple devices, and the rest are kind of split between legacy and the newer Androids. Now, what's interesting about it? Well, for easy content, turn out that if you try to stay with only few renditions and try to deliver best quality, then up till the point when you have 6 renditions, if you only have like 5 renditions that you could encode, it turns out that using H.264 only is the solution. If you only have 5 streams, adding any extra HEVC streams is not going to help you on overall. But starting from 6 streams, it actually does help, and it does help quite significantly. So if you look at the bit rates that we achieve, at quality that we achieve at 6.6 streams with this mixed profile, well, it is equivalent to the quality achievable with 6-stream H.264 only profile, right? but then bitrate will be like 40% less. It's 1050 versus 1445. So this mixed ladder has dramatic utility. Or another interesting example, let's look at 7-point ladder and look at quality that's achievable there. So at 7 points, this hybrid ladder gives same quality as 8-point H.264 only ladder, fewer renditions. Plus, if you want to design just 2 ladders separately, you will design this one with 8 rendition, and then you will also need to throw 4-point HEVC ladder to match them. So you need almost twice number of rendition total to get to the same average quality as a mixed ladder in this case. And for complex content, it's actually even more dramatic. But one important difference that we notice right away is that with easy content, if you have only few renditions, H.264 only was the regime. With complex content, even if you have 3 renditions, it turns out it makes sense to start blending HEVC streams. And then the savings are quite dramatic. So for example, 5-point ladder with 3 HEVC streams and 2 H.264 streams deliver about same quality as 8-point ladder from H.264 plus 2-stream ladder from HEVC. So 10 streams total to
I got confused about, what's the difference between Q-sub-N and Q? Oh, what's it,
okay.
is this now working? Or are you trying to, you're tricking me?
Yeah,
Okay,
yeah,
Q-sub-N
and average Q. Q-sub-N is a quality at the last rendition, and Q bar is average quality.
Okay, so that's the thing you're trying to optimize.
Yeah,
that
yeah,
last one.
I'm optimizing for average, but just for reference, I'm also including the quality up top rendition.
So I have a question here.
Yes.
If the quality level is coming out same, the average quality, right? Why not just use 2 separate ladders for H.264 and HEVC instead of creating a new one, new ladder, which is a combined one, and then write a complex manifest filtering logic?
Well, because you can do same quality with fewer renditions. Here with 5 renditions, you will achieve same average quality as you will achieve with 10 if you just design to optimal ladders for each separate codecs by themselves.
And the reason is that, I'm just trying to get your viewpoint. The reason is that because we cannot get away from H.264.
Because you cannot get away from H.264, and look, the difference in number of renditions is actually dramatic in terms of your encoding costs. It's also dramatic in terms of your delivery costs, because what happens with these renditions, they go to CDN edge cache, and they start competing between each other. And so the more renditions you have on edge cache, the higher the probability they're not going to stay there, and you're going to be pulling all the way from the origin, and you will be paying 10 times more for your egress costs. So it's really a long way how the reduction in number of rendition goes in terms of improving performance of and reducing the costs of your system. So that's the utility. So quite dramatic reductions in a number of renditions, and that's just one utility that could be achieved. But of course, you could optimize it in a variety of other ways. You could look at your overall cost. Your final figure of metric could be very complex expression, including multiple cost components and as well as multiple quality components. Here I'm just looking at average as a simple mathematic model. So just for record, this was all published. You could find long papers on each of these topics. And now just a few minutes to say that it actually all works. And of course, it all works in Brightcove video cloud system, which is basically an end-to-end delivery system. It's cloud-based. It includes transcoder as encoder. It includes dynamic, what we call dynamic delivery system, which is basically transmaxing, real-time transmaxing and manifest generation logic, CDN coupling, players, and it's all connected by analytics module. And what is important is that the information from analytics is used in feedback loop to CAE, and CAE is our context-aware encoding. That's the profile generator, effectively. So all these profiles that I was showing how to produce using Mathematica and some models, we actually have implemented as a operational piece of software that sits in the context of this system. And this is how it looks in practice. So you could pick one of the presets. It's called context-aware encoding, or you could write a JSON like a constraint set to this generator, where you could specify which codecs you want to use, what resolutions you want to use, other constraints. Network histograms can also be glued there, and so it's a pretty evolved JSON syntax of parameters that could be passed to the system, and it works. So I'll show a couple of results of performance of this system in two cases. So first case is we look at, it's the same content. It's a moving content sent to 3 different operators. So the first operator is in Asia, and it sends mostly streams to mobile, like 94%. And if you look at average bandwidth across all devices, it boils down to about 3 megabits. It's a very poor case of very poor networks. And the system is really struggling in many cases delivering data to delivering high quality video to this type of operator. And if you look at network statistics, they have huge peak at very low bit rates and extra peaks down there. The second operator is a US operator. It streams to a blend of devices. PCs take about 63%, but TVs about 20%, and mobiles somewhere in between. The average bandwidth across all the devices is about 16 megabits. Of course, for TVs, it goes to 24, much more luxurious. And you look at the bandwidth distributions, they're, of course, much more spread. The third operator is the operator in Japan. It streams predominantly to TVs, and the average bandwidth there is 35 megabits. But if you look at the distribution, you see huge tail here going all the way to 100 megabits. It's wonderful networks. We can only dream about having these types of connections here. So totally different operators, but what we do is we send same content to them. We measure statistics and see what benefits will be if we apply CA optimization. So and CAE, of course, generates different profiles to all of them. And this is what you could see. So we save number of renditions to all of them, but remarkably to operator 3, which has best network, we save the most. We save like 44% in renditions. Effectively from 9 in standard HLS ladder, it went to about 4 or 5. And the reason being is that if the network is fantastic, it pulls the top rendition with 99% probability. The other renditions that you need to include in ladder is for conformance with HLS guidelines, saying that you need to step in increments of 100%. Stuff like this. You still need to include the streams to pass certain conformance tests, but you really don't need it if you think about what is being pulled. But still. Now, in terms of storage, of course, the last operator has most dramatic savings, 68%. Actually, all operators have significant savings, well over 50%. Now, in terms of bandwidth, this is interesting. So for operator 2 and 3, where they had like 16 to 30 megabits of bandwidth on average, we save about 30-something percent. But for operator 1, which had very constrained bandwidth, we can't save much. Why? Because even if we encode more efficiently, we pick resolutions to match its bitrate more efficiently, it's just going to eat whatever you give it. It basically pulls all the data to maximize capacity of the network. So we still save something. It's about 8%, but not as significant in the other cases. But then if you look at average resolution, turns out that net effect for this operator is very significant. We increase number of pixels by about 27%. So it uses slightly less bits, not as much savings in bits, but the better choices of resolutions give better quality of experience in that case. And for other operators, of course, those savings less significant. There are also savings in things like buffering, startup time, but single digits. SSAM values across all, remarkably enough, very close. It's a
savings compared to what?
the reference encoding in all cases was recommended HLS guidelines profile.
They're just taking the profile that HLS
Exactly.
recommended and versus the
versus
supplements.
the supplements. Now, the next example is try to study and quantify efficiency of the system considering different types of content. So what we did is we basically pulled about 120 hours of programming from major customers of ours, and we split it in assets, and there were about 500 assets, and we did categorization of these assets to 35 or 34 different types. For example, different kinds of sports, different kinds of movies, adventure, comedy, drama, soap opera, and so on. And so it was manual classifications. We literally looked through it, and then we did summary statistics across each category to see what savings we will see across different categories of content. And reference profile was this. This is the same profile in that case. It's a standard Apple HLS profile. And what you could see is that the savings are quite different for different types of content.
Yuri, so forgive me, but the reference profile, this is the Apple technical note.
Yeah.
Nobody uses that in the real world. Right.
Lots of people are using it.
Nobody who's doing large amounts of video is using that. So this seems like a best case illustration. I'm not disputing the numbers at all, but it seems like you're optimistic in terms of the actual savings that you'll see because people are optimizing the profiles based on the content that they have.
You're right. These are savings relative to this profile. For those customers who are using this profile, this will be exact match. For those who use something else, it could still be of value in relative sense, because you could see what could be the totals for this and compute yours. But it's actually been used by a number of customers of ours and still being used, remarkably enough. But in any case, what I wanted to say about different categories is this. Of course, for slowly moving content, things like soap operas, movies, dramas, and such, we see savings well over 50%. For sports, it's actually different. So there are sports that are complex and there are sports that are easy. For example, for hockey, we are somewhere in 20s. For swimming is the toughest one, turns out. It's not only lots of waters and splashes, it's also short like segments of runs that athletes are doing and swimmers are doing, and it all in combination makes it very challenging. So we still save about, what is swimming? About 19% in that case, but that's actually most challenging content in this case. But on the other hand, for golf, we're saving 72%. And why we're saving a lot for golf? Well, because there is lots of static imaging in golf. It takes a time for golfer to prepare, to take a right position, right? And these are lots of static pixels that could be compressed much more efficiently. So basically, and you see it's a saving in storage, in number of streams, in bandwidth, and we actually gain in resolution as well across all of them. So pretty good outlook. Conclusions. We started with multi-profiles, and it's certainly a lot of fun. It connects to classical results, bring high potentials for improvements in practice. It plays well to the trend and dynamics in industry to make clients switchable. But of course, there are many other details and more fun to anticipate in the future. Consider the case of H.264 and HEVC, right? There is coming AV1, there is VVC coming, there is also VP9. AV2 is another one that's coming. Of course, with H.264 and HEVCs were three categories of clients. There was one that can decode one, another that can decode the other, and the third one that can switch. So once you start factoring this new codecs, it will be more complicated. Right? Some devices will be able to decode this codec in that circumstances, not in another circumstances. There could also be some licensing constraints. I can easily envision a situation where there will be business logic deciding, do we allow certain streams encoded in this format to go if we have a choice to deliver in another format, and so on. So there will be certainly more work and more fun. And on this note, thank you very much.